So you guys are going to fill in a lot of the details because it's going to rhyme with what we did last time. But we're going to talk about Laplace's equation. And the only difference in between what we finished before a little detour into Hermite polynomials and the oscillator was solving Laplace's equation for spherical polar coordinates. We did it in two chunks, azimuthal symmetry versus not, but that was just solving this. Oops. Let's say f equals 0. Now we're going to talk about that in the case where whatever symmetry of the system makes us want to use cylindrical polar coordinates. So f is now a function of rho, phi, and z. Okay. Before we get into that, there's one pretty, I don't know if it's obvious because you don't really think about this too much. Anybody think of an example where you might want to have Laplace's equation or something very similar to it, specifically the Helmholtz equation, in cylindrical coordinates? Which is to say, things that have a cylindrical symmetry.
A lot of portable speakers are like cylinders. I don't know if you're solving the wave equation. I don't know.
So wave equation, anything that's cylindrical that makes sound, including drum heads, in fact. So until the stuff starts spreading out, if you have a circular membrane and it's constrained to, kind of be stuck around the edges, specifically the wave equation is what's called Helmholtz equation, but it looks so close to this that you can still use Bessel functions mathematically. So I'll just say speaker or drum head. And that's going to be something that looks like this. So technically that's the Helmholtz or wave equation. Anything else? Anybody do any electrical engineering stuff? Or have any old analog TV or computer equipment? So coaxial cables and waveguides. So in that case, you have an electromagnetic potential, an electric potential potentially, and you want to solve that, but then the coax cable is something that looks like this, where you've got a current going through wire and then you're trying to shield it, so you've got some boundary conditions. So this is important. It's not just like us torturing you by saying yeah, let's just go through every single possible coordinate system. Okay, so this is what I need to do. Want to solve that. I have to go back and talk about what the Laplacian is in spherical polar coordinates. I'm going to have a bunch of goofy scale factors to deal with the rho and the phi part. We know how to do that. I'm going to kind of gloss over it. And I'm just going to write down the answer. And hopefully you guys are not surprised by its form, right? The fact that this isn't just d by d rho squared plus d by d phi squared plus d by dz squared, like it would be in Cartesian coordinates. We have some scale factor business to deal with. So rho. So this is the Laplacian on f, where we're using f as a scalar function. So f sub rho, for instance, the only thing that could mean is partial f with respect to rho. And f sub z, the only thing that could mean is partial f with respect to z, because again, it's a scalar function. Okay, so here's the thing that we want to solve and find solutions of. And you've been through a differential equations class. Each of these individual terms don't look bad, but it's got derivatives with respect to rho, phi, and z. Help, what should we do? So this is the part where I want you guys to at least take over, and then I'll write the first step and the last step, because everything in between should be pretty, we've covered. So how do I start solving this?
Since all of that is equal to 0, you could like put all the terms with like one like derivatives with respect to one variable on one side and derivatives with respect to the other two on the other, and then say that both of them are constant.
Yes. So first thing is correct the fact that I should have said equals 0, because that's what we're solving. There's something that we have to do first before being able to isolate stuff. So for instance, right now, f sub zz, this last term, which looks like, it's totally just asking to be picked apart and put on the other side. This is two partial derivatives with respect to z of f of rho, phi, and z, right? Remember, f is a function of rho, phi, and z. So even if I put it on the other side, it's still a function of rho and phi. So I can't make that argument quite yet. I have to do one super important thing first.
Express f as a product of 3 different functions, each of which is single variable.
Yes, so I have to separate variables. So I assume the solution looks like this. I have no idea I don't think there's a capital rho, so we'll call it R of rho. And then we'll call capital phi is also annoying since we've already broken protocol. I'll call it A of phi. And then we'll just capital Z, I think I can do Z of Z. So this only works if I assume that the solution is separable. And so now when I put this form in, I get something that looks like this, 1 over rho rho r prime a prime z. So I don't have to worry about writing the dependence on the variables because it's obvious. R is only a function of rho, a is only a function of phi. 1 over rho squared r a double prime z, and then r a z double prime equals 0. Okay, so now what I can do is I can start trying to separate stuff. Yeah, but you need that something that I have separable solutions. Okay, so the typical way of doing this is you take the whole thing and then you divide by RAZ. And what you can see is that I'm going to have the underivatived terms vanish, right? So the R and the A go away. I end up with Z double prime over Z, and I end up with A double prime over A here, and I end up with R prime, but other stuff's going to happen to it over R there. And then I think you erase something. There should be a, no, that's a, oops, there's a D row there. There's a missing D row there. Here. Okay. So really important, any questions about that? So I'm just gonna write down a format. I'm gonna tell you what you should choose the separation constants to be. Again, this is one of the few things where it's like, if you choose them yourself, you won't be wrong. You just might give yourself a little bit more work than you wanted. So this is the traditional way of separating what will ultimately lead us to Bessel's equation. Is that absolutely right? The first piece to pick on would be the z piece. It's all by itself. I put this stuff on one side and I put this stuff on the other side. And if this is equal to negative that, so z double prime over z is equal to that for any choice of variables, you choose phi and rho and I choose z, and all of a sudden 1, 2, 3, we reveal our choices. No matter what they are, this equals negative that. Obviously, they're equal to a constant. That's the only way that that could happen. This is what you should choose the constants to be. So first separate z and call the separation constant k squared, something squared, some integer squared. And then this would therefore be equal to minus k squared. Okay, so this gives us our first differential equation, ordinary differential equation. Remember, ordinary differential equation means just one variable, and it's z double prime equals k squared z. Okay. And depending on what you want to do, you can put all of this stuff on one side or all of the other stuff on one side. So this is kind of your choice. You could do plus or minus. Usually what happens is the physics tells you which one to do. So if you're oscillating, you should probably use a negative sign. And you go off to infinity, you should use a positive sign. So we'll just say choose sign based on physics. Okay, I hope you guys can solve this differential equation, but I want to write down the most general form. So the most general form, let's say that we have, for instance, negatives. So let's say our physics tells us that we should have minus kz. Okay, what is the sort of function that satisfies two derivatives of the function, bring out a constant each time I take a derivative, but then I also get a negative sign? So again, if we have a minus sign, two derivatives, I get back my original function, but with a negative constant. What must it be? I think there are really three answers, all of which are fine.
A sine, cosine, or an exponential.
Yeah. Okay, let me ask you guys this then. It's kind of a follow-up question. Let's say that I do have, let's talk about like a coaxial cable or a waveguide or something like that. And I'm putting like a signal through this. And so it's going to be really hard to draw, so bear with me, or this isn't going to, it's going to be a cartoon of what's really going on. Is I have some signal that depends on z. It's some, you know, if you think about it being time dependent, some moment in time, or you could think about, you know, like air trapped in a tube, like somebody playing a single note on a flute or a clarinet or something like that. That's also, you know, the standing wave in a clarinet might be a good thing to visualize. And I have z of z. And z of z is kind of funky looking if it's an electric signal. It's not necessarily a sine or a cosine, but it's totally valid. My solution says that this be cosine something k z, or sine is the answer. How would I make some arbitrary function that maybe were my initial conditions out of this, what seems to be the solution? So you talked about it and maybe you thought it wouldn't come back into your lives, but here it is. What is the most general solution, actually? Remembering that you don't necessarily know that k is one single value. K is just some separation constant. K could be 1, 2, 3, 4. So in fact, what do I really need to do if I want to represent some arbitrary function? So the full and total solution, because again, k was just like something we kind of made up. If I put in real boundary conditions, I won't tell you what this is yet because we haven't shown it, but k is equal to sum over all the possible allowable k's, cosine kz plus a k sine kz. That's an awful looking sign. So in fact, what we've got is that because we don't know what k is, it's not some value like it was with the simple harmonic oscillator, the actual mechanics, not quantum mechanical one. K was chosen at the hardware store with like a spring constant and a mass. Here, it's just something to do with this differential equation. So in fact, our most general solution is going to be a sum over all possible values of k. What does that look like? That looks like a Fourier series. Okay, so you cannot escape this. Okay, so that is the solution of just this part. So now we have to keep separating. So we have the part on the other side, and we have minus k squared equals 1 over rho r prime over r plus L prime over r. Okay, so this will be the second and the third ordinary differential equation. We got to get r by itself, or a, whatever. I think it seems easier to think about a. So we've got to multiply by rho in order to separate this. So this turns into the separable differential equation, a double prime over a equals minus k squared rho squared. Oops. Yeah, this is a squared. K squared rho squared minus rho r prime over r, and then minus rho squared r. Yep. Okay, so now this is separated. We pull the same stunt. I will tell you what you should choose for the separation constant. Although honestly, like I don't know why I'm explaining it like it's some sort of like mystery handed down by divine oracles. We have two derivatives. So we have two derivatives, so we should choose something squared. I guess if there is something that's a little bit not obvious, it's you can choose things to be squared in one of two ways. We could choose like m times m minus 1, because we're going to get a polynomial solution and powers keep dropping, or we can choose things to be just like straight up m squared. So if there is a little bit of obscurity about how you should choose your constant. I guess it's really that. Okay, in this case, we should choose m squareds. So we'll call this minus m squared and m squared. So that is what I'm telling you you should choose as a constant. Okay, now we have the azimuthal part of the solution, a double prime over a. Really nice to deal with. And then we have this thing. This is super gross. Okay. With the one aside that, yes, it's true that these are sines, cosines, and exponentials, but because k can take on a number of different values, what we really kind of have is a Fourier series. That's the exact same thing that's going to go on with this. So the azimuthal part is going to be Fourier series made up of a whole bunch of sines and cosines. This is what we want to spend time on. So this is Bessel's equation. This is a new thing that does not have an obvious solution. It's kind of gross. So this is what's going on with the radial part. And if I imagine like kind of modes of a drum head, I might see them oscillate like this. If you really want to think about Bessel functions, I think the best way of thinking about it is those really cool pictures of a raindrop splashing into still water, and then the ripples that come out, and the ripples spread out and they get successively smaller. That's a Bessel function. So this is the raindrop differential equation, essentially. Okay, so same thing though, we just separated, and maybe there's a little bit of nudging about what to choose as a separation constants. Any questions about that? Because now we're going to talk about Bessel functions. Okay. So we did it the physics way. There are different forms of Bessel's equation. They're not significantly different. I'm going to clean this up a little bit. And I'm going to note that because we had two different separations of variables, we end up with two different constants. So Bessel's equation, keeping the r's in rows and k's and m's, looks like this. So you're on a desert island, you want to solve this differential equation. Somebody just tells you that like k is something and m is something, 2 and 4, I don't know. How would you solve this? And answer knowing that I'm not going to make you actually, do that.
I'd probably assume like an exponential solution and then try to find like a characteristic equation.
Yep. So one way or another, that's a perfectly fine one to start with, is we'll just try a trial function. And a trial function could be an exponential. A trial function could be a power series. A trial function could be the funky thing that we did with Hermite polynomials, which is to do both in some sense. So just pick a trial function and throw it in there. The reason I'm skeptical that the trial function isn't something super simple is that we wouldn't have things called Bessel functions if they were just like sines or cosines or something like that. So there's kind of this sociological, like maybe there's something like awful. So let's just maybe do the most general thing that we can do and say that there's a power series solution. So in fact, there's a power series solution and it doesn't really have any asymptotic behavior. So we just like straight up try a polynomial. Okay, But yeah, try a trial function, throw it in and see what happens. So we'll try a trial function. Okay, the first, yeah, I don't know when the best, yeah, whatever, let's just solve it without naming stuff. So there's a little bit of a caveat here. We didn't have to deal with this with the harmonic oscillator, is that we blow up at rho equals 0. Right. So we have solutions that may possibly blow up, and so we need to accommodate those. So when we use the most general trial function we can, let's call it y of x. And use the method of Frobenius, we're going to have potentially functions that blow up. So this means that we don't necessarily have r equals 0 at the outset. But after you plug this in, it turns out you find out what r equals pretty quickly. Okay. So the next step is to develop an indicial equation, which is to just throw this thing in, and you end up with this, AL equals minus AL minus 2. Actually, I shouldn't write it like that. Just write it the way that we wrote our other one. I'll just call it N, whatever. So the indicial equation gives you some number. I want to describe the properties of how this thing blows up or doesn't blow up. This is also work for you guys on the homework. So N is determined by K's and M's. And the indicial equation actually looks kind of nice by itself. Looks something like this. So in this case, we have an issue in the denominator instead of the numerator. Right. So in this case, we need to truncate a series to keep it from, at low numbers, to keep it from blowing up. And high numbers, we're going to end up with a sum that goes all the way to infinity, because we have this thing grows like 1 over L squared, and 1 over L squared converges. So our issue is that we don't want this thing to explode at low L's. So the truncation is determined by L and M. And if we're going to sum from L equals 0, so looking at the L equals 0 term, that means that R needs to be equal to plus or minus N. So not 0, but something to do with these. And that's when you do the indicial equation on the homework, you'll find out what N is. So Y1 could try this. It's not going to be as easy. Well, I don't know. I think it is going to be as easy as the Hermite polynomials because we don't actually have to solve all of the terms. I just have to write down the series. So we're going to have y1, for instance, which means that r equals n equals 1. Is going to be the sum from L equals 0 to infinity of -1 over L squared A oops, let me do this in 2 steps, sorry. Sum from L equals 0, AL, X, L, plus or minus N. So our series is going to take on that form, and therefore we're going to have to, oops. I'm like reading 2 lines of my notes at once. Need more table space. Okay, so this is the form of our series. So we're going to have an infinite number of terms. We don't have to worry about it truncating at the high end. We have to worry about it truncating at the low end. And therefore, we should subscript our solutions by the value of n. So instead of the Hermite polynomial game, where you tell me where to stop, and that labels my solution, we're playing this game where you tell me where to start, and we label n by that. Okay. So what you can show is with some, I'll just say can show. You would play the same game where you choose a naught to be 0, for instance, or in this case, a naught to be 0, and then I can find a1, a2, a3, a4, all the way out to infinity. Because you're plugging the same number in over and over, there should be a recursive formula. I will write down the recursive formula for n's. So we have y x, xn. Okay, so you choose a naught, that's still a free parameter, but then after that, you know, a naught keeps getting multiplied by a succession of constants. So that's n plus L. So this is the polynomial. There's the polynomial form, and then there's this set of coefficients out front, 2L. This is what's called the Bessel function of the first type, and this is the point at which we give it a name and denote it by Jx. Okay. So these are what are called Bessel functions of the first type, the solutions of these. They have recursion formulas, they have orthogonality properties. I'm just going to bring up what they look like. The thing that's left to do is fill in the details of the development of the indicial equation. And then honestly, after that, it's just when would they show up? So we'll do like a full example of how to develop a differential equation and then find, you know, this is the way it works, is that you say like, there it is, I see Bessel's equation in this, and I know what the solutions are. So my Mathematica is taking its sweet time. Okay, can you guys see that now?
Yep.
Okay. So the good news is that these should all be coded into any MATLAB or Mathematica. And the way that it works is the second you see Bessel's equation, you can say like, aha, I've got Bessel function solutions. So this is just bolden that up a bit. Okay. So the thing that you have to know about them is that we had a parameter n. And what you guys are left to do is figure out what n has to do with k and m, the separation constants. And it turns out that you won't be surprised that this thing might actually have fractional values. But remember, because we have a separation constant too, in fact, we have a free parameter. So the way that you should think about these, let's see if I can annotate directly on this, is raindrop falling in a pond. So I have a bunch of circular waves caused by a drop of water falling in a pond, and the height of the water should look like this as I look in the radial direction. So that's exactly what these Bessel functions look like. Okay, they're kind of circular sines and cosines, if you will. And let's see what else I put on this. Yeah, let's not talk about complex stuff yet. So within Mathematica, at least, let's say that I hard coded in that thing above, Bessel's. This is Bessel's equation. So this is the differential equation. We had two derivatives times x squared, and then we had the one derivative, and then I have this. Mathematica will recognize that and say, like, you just typed in Bessel's equation. So it should give you the solutions. Okay, so that's where it is. You can plot some of that. I think that's actually asked for in the last part of homework 7A. So the rest of what we want to do is, there's not enough time today, but on Tuesday, we'll develop from scratch a physics problem. I think a rotating string, we'll do it. So we'll take a rotating string from scratch, write down Newton's second law, and then show how this thing shows up. But really quickly, I just want to show that, surprise, surprise, this thing has some properties. I'm going to write it down, and some terminology associated with it. But any questions about that so far? Okay, so this is what we have. We have, quite frankly, gnarly series solutions for Bessel's equation. And for somewhat, oh, no, it's useful. So we have Jn of x. Remember, n has to do with our separation constants. Those L's weren't looking really nice, so I'll just relabel this S. and we can shuffle that x in. So this is the series solution. That's what was making those raindrop radial patterns. Turns out that n's come in pairs. We can have n be positive or negative. Remember, those separation constants could be positive or negative. Absolutely or negative. And we have recursion formulas. And the recursion formula for a Bessel function is actually much nicer. So honestly, all the terrible part is the fact that you have an infinite series and you have to do this kind of leap of series arithmetic to get these closed form solutions. But after that, Bessel functions look and act pretty well behaved. We're actually going to have to work to make them act not well behaved if we need them to go to infinity. So if I want to know the n plus first Bessel function, I can do this on the n minus first and nth Bessel function. There's also a parity formula, but you can see that pretty easily. Okay, so what's left is we'll see how this would show up in at least one physics context. I think mechanics is the easiest to visualize, but if you guys want to do cylindrical waveguides or something like that, I guess we could do that. But any questions about that? So that's 3 examples of differential equations that we solved by separating variables, getting the hardest one into a format of an ODE, and using a variety of different methods. Inspiration, Frobenius's method of assuming there's a power series. And I did ... the closed form solution getting to these 2 up there because it doesn't teach you anything. And the step before that of generating those is the homework. So basically just kind of grinding through and finding the indicial equation. So any questions about that? Cool. I would like to now, partly just